Hello everyone, and welcome to Class 12. I'm recording this one for you because I'm out of town, but everything you need is right here. So settle in and treat this exactly like a normal class session. Today we begin Week 4, and we move into Division 07, specifically insulation systems and thermal performance. Here's why this matters before we even get into the materials. Insulation is one of those parts of a building that's completely invisible once the walls are closed up, but it drives energy cost, occupant comfort, moisture behavior, and whether the building even passes code. As a project engineer, you'll be checking insulation submittals, verifying it's installed correctly before drywall covers it, and coordinating it with the air and vapor barriers. So this is a working knowledge you'll use, not just test material. We're going to cover the 4 big insulation families: batt, blown-in, spray foam, and rigid board. Then we'll dig into R value and actually calculate a wall assembly together. And then we'll spend real time on 2 failure modes that trip up new people: compression loss and thermal bridging. After that, we'll walk insulation location by location: attic, wall, slab edge, cathedral ceiling, foundation, crawl space, and finish with participation assignment 12. Here's our roadmap. 8 blocks. We start with why insulation matters. The 4 drivers are energy code, comfort, moisture control, and condensation risk. Then the 4 insulation types: batt and roll, blown in, spray polyurethane foam, and rigid board. Block 6 is R value, the key metric, what it means, how to calculate series thermal resistance, and code minimums. Then compression loss, which is a specification failure, not just sloppy work. And we close with participation assignment 12. Look at the diagram on the right, and keep these 4 ideas in your head all class. Heat flows from warm to cold through the building assembly. Always, every time, that's physics. Air leakage carries heat and moisture through the assembly. A thermal bridge is a material with higher conductivity that creates a shortcut path for heat. And condensation risk happens when warm, moist air hits a cold surface. Every material and every detail we discuss today is trying to manage one or more of those 4 things: control heat flow, reduce air leakage, limit condensation, and improve comfort. Now the 4 families. I want you to learn each one by 3 things: what it is, where it belongs, and its one big caution. Let's go. Batt and roll is your classic fiberglass or mineral wool, pre-cut or cut to fit, placed between studs and joists. Fiberglass runs about R 3.2 to R 3.8 per inch. Mineral wool is a little higher, R 3.7 to R 4.2 per inch. It can be craft-faced, foil-faced, or unfaced. The facing is the vapor retarder, and which way it faces matters. Best uses: standard wall cavities, floor cavities, regular framing spacing. It's the lowest cost option, widely available, easy to install with common tools, and every trade knows it. Here's the big caution, and it's the theme of a whole slide later. Batt must be cut accurately and installed without gaps or compression. A batt that's stuffed, crammed around wires, or left with gaps does not deliver its rated R value. The number on the package assumes a perfect, full loft installation. Blown in is loose-fill cellulose or fiberglass, machine blown into attics or dense packed into closed wall cavities. R value runs about R 2.2 to R 3.8 per inch, depending on material and density. Its superpower is filling irregular voids and hard-to-reach spaces that batts simply can't, around odd framing, into existing walls. That makes it the best retrofit option on the board. The caution: depth and density have to be controlled, and settling matters. Loose fill can settle over time and lose thickness, so it has to be installed to the right depth to account for that. Spray foam is a 2-component liquid that expands in place and adheres to the substrate. There are 2 kinds, and you need to know the difference. Open cell is about R 3.7 per inch. Closed cell is about R 6.5 per inch, nearly double. Best uses: rim joists, irregular spaces, air sealing, roof decks, high-performance assemblies. Its big advantage is that it does 2 jobs at once: air sealing and insulation in one application. and it conforms to complex shapes and fills voids. High R value per inch, especially closed cell. The caution here is real. SPF requires trained installers, and open cell and closed cell have different vapor and moisture behavior. Closed cell is denser, higher R, and can act as a vapor retarder. Open cell is lighter, more vapor open. Using the wrong one in the wrong climate or location can trap moisture, so this is not a guess and spray product. Rigid board is factory-formed boards, adhered or mechanically fastened, and it's most often used as continuous insulation. 3 common types with different R values per inch. EPS at about R, 3.8 per inch, XPS at about R, 5.0 per inch, and polyiso at about R, 6.0 to R, 6.5 per inch. Best uses: exterior continuous insulation, roof insulation, below-grade and basement walls, and, this is the key one, thermal bridge control. High R value per inch provides continuous insulation, reduces thermal bridging. The caution: seams, attachment, and moisture compatibility all have to be detailed correctly. The bottom of the slide gives you the cheat sheet. Lowest cost: bat and roll. Best for retrofits: blown in. Best air sealing: spray foam. Best thermal bridge control: rigid board. And the best practice line ties it together. Choose insulation based on the cavity condition, moisture exposure, air sealing needs, and the required R value. There's no single best product. There's a best product for the situation. Now the key metric, R value. 4 principles across the top, and they're the foundation for everything. R value is resistance to heat flow. Higher R means better insulating performance. R values in series add together. That's the one we're going to use to do a calculation. And compression, thermal bridging, and air leakage all reduce real-world performance below the number on paper. Let's actually calculate a wall. This is a 2x6 wall assembly, and we're going to add up the layers from inside to outside. Interior gypsum board, 5/8 inch, R, 0.56. Interior air film, R, 0.68. Yes, even the thin film of still air against the wall has a resistance value. The 2x6 stud cavity with bad insulation, R, 19.0, the big one. OSB sheathing, 7/16, R, 0.62. 1 inch of XPS rigid board, continuous, R, 5.0. And the exterior air film, R, 0.17. Because resistances in series add, we just sum them. 0.56 plus 0.68 plus 19.0 plus 0.62 plus 5.0 plus 0.17. That comes to approximately R, 26.0 for the total assembly. That's the whole wall R value. And notice it's higher than the R, 19 bat alone, because every layer, even the air films, contributes. This is exactly the kind of calculation you'll do on the participation assignment, so make sure you're comfortable with it. Identify each layer, find its R value, add them up. On the right are typical code minimums. We're in Climate Zone 2 here in Texas, so these ICC example values apply. Above-grade walls want roughly R, 13 in the cavity plus R, 3 continuous, or R, 20 in the cavity. Attic or roof, R, 49. Floor over unconditioned space, R, 19. Basement walls, R, 15 continuous, or R, 19 cavity. Slab edge, R, 10 for 2 feet of depth. And the note matters. Always verify the current local code amendments and the adopted ICC edition, because these numbers change and jurisdictions amend them. And the bottom right box previews our next 2 slides. Installed R value drops because of compression loss, thermal bridging, and air leakage or moisture. The CM field check at the very bottom is your job in one line. Verify insulation type, thickness, cavity fit, continuity, and vapor/air barrier coordination. That's what you're checking when you walk a job before drywall. This slide is about a specific, common, and totally avoidable failure, compression loss. Look at the 2 pictures. On the left, the correct fit, a 6.25-inch bat in a 5.5-inch 2x6 cavity. A nominal fit, fibers hold their designed air pockets, and the rated value is approximately maintained. On the right, the compressed fit. Someone took that same 6.25-inch bat and forced it into a 3.5-inch 2x4 cavity. The fibers are packed tighter, there's less trapped air, and that means lower thermal resistance. Here's the mechanism, and this is the part students miss. Bat insulation gets its rated R value from two things: its thickness and the still air trapped inside the fibers. When you compress it, you pack the fibers tighter and squeeze out that trapped air, and the trapped air is what's actually doing the insulating. So you lose R value. An R19 bat crammed into a 2x4 cavity doesn't perform at R19. It performs closer to R13 or even less. The rule of thumb is simple: match the bat to the cavity depth. R13 for 2x4 walls, R19 for 2x6 walls. Do not stuff a thicker bat into a thinner cavity thinking you're getting bonus insulation. You're not. You're getting less than the cavity could hold, and you've wasted material doing it. Box 3 is your job again. As the CM or inspector, verify the framing depth, the specified bat thickness, and that the submittal matches before installation. And the table at the bottom makes it concrete. A 2x4 cavity with an R13 bat is a correct fit, good outcome. A 2x6 cavity with an R19 bat is a correct fit, good outcome. But a 2x4 cavity with an R19 bat is compressed, bad outcome. The takeaway line says it best. Compression is a specification and installation failure. The labeled R value does not automatically carry over when thickness is reduced. Second, failure mode. And it's sneakier than compression because the insulation is installed perfectly and you still lose performance. Thermal bridging. Look at panel A. Cavity insulation only. The studs conduct heat faster than the insulation around them. They are literally bridges for heat to cross the wall. So the whole wall R value ends up lower than the cavity R value. You've got R19 bat in the cavity, but the effective whole wall performance drops to about R14 to R15 because framing might be roughly 15 to 25% of the wall area, and at every stud, heat takes the shortcut. Panel B is the solution. Add a continuous layer of rigid board on the exterior, continuous insulation, what the codes call CI. Because it's continuous, it covers the studs too, so the heat shortcut through the framing gets interrupted. That continuous layer improves the effective whole wall performance, and that's exactly why energy codes increasingly require continuous insulation. Remember the code line from 2 slides ago: R13 cavity plus R3 continuous? That R3 continuous is there to defeat thermal bridging. The key principle is in that highlighted box. Cavity R value alone does not equal whole wall R value. Continuous insulation is the standard solution to thermal bridging. Burn that into memory. It's a favorite exam idea and a real-world coordination issue. Where does thermal bridging show up? Wall studs, floor joists, roof rafters, shelf angles, parapets, and steel framing interfaces. And note this, steel is a much stronger thermal bridge than wood because steel conducts heat far better. The examples table ranks them. A wood stud wall is a moderate bridge, a steel stud wall is severe, a slab edge or balcony is a major bridge and a real condensation risk, and metal shelf angles and lintels at openings are high-severity local bridges. The warning at the bottom. Ignoring thermal bridging can undermine code compliance, comfort, and condensation control even when the cavity insulation meets the specified R value. Now we tour the building location by location, because where insulation goes changes how it behaves. First, the vented attic. The big idea. In a vented attic, the insulation goes on the attic floor, at the ceiling plane, and the attic space above stays ventilated. So the thermal boundary is at the ceiling, and the attic above is essentially outside the conditioned envelope. Walk the airflow. Air comes in low at the soffit vents at the eaves, flows up through a ventilation channel kept open by baffles, and exhausts high at the ridge vent. The insulation, blown in or bad, sits down on the attic floor at the ceiling plane. 2 details that matter enormously. Number 1, air seal all penetrations before you insulate. recessed lights, pipes, wiring, because insulation does not stop air leakage, and a hidden air leak under the insulation defeats it. Number 2, the baffle or ventilation chute keeps the airflow channel open above the insulation so the insulation doesn't choke off the soffit vents. Key installation rules. Air seal penetrations first. Maintain the ventilation channel at the eaves. Install baffles before insulation. Insulate and weather strip the attic hatch. And don't compress the insulation unnecessarily. There's our compression theme again. The common mistakes panel is the mirror image, blocking soffit vents, skipping air sealing, insulating the roof deck instead of the ceiling plane in a vented attic, and leaving gaps around the access hatch. That last detail, people insulate a whole attic beautifully and then leave the hatch bare, and it's a giant hole in the thermal envelope. Next location, the above-grade exterior wall, the one we calculated earlier. Bad insulation in the stud cavity is standard practice, and continuous rigid insulation on the exterior reduces thermal bridging through the studs and improves whole wall performance, exactly what we just covered. The note about spray foam at rim joists matters too. Rim joists and other irregular air leakage locations often get spray foam to improve air sealing and thermal continuity, because bats don't seal those awkward spots well. Read the wall from inside out. Interior gypsum board, an optional interior vapor retarder if used, the wood or metal stud wall with bad insulation in the cavity, structural sheathing like OSB or plywood, the water-resistive barrier or air barrier, the continuous rigid insulation board, a furring or attachment system if needed, and finally the exterior cladding, siding, brick, whatever the project uses. Here's an important field note, and it's climate dependent. If a vapor retarder is used, it typically faces the warm in winter side. In a cold climate, that's the interior. In a hot, humid climate, it can be the opposite, which is why you always verify local code and climate zone requirements rather than assuming. Don't put a vapor retarder on both sides. That traps moisture with nowhere to dry. Why it matters: reduces heat loss and energy use, improves comfort, manages condensation risk within the wall, and helps meet energy code. Your CM field check. Verify the bat fits the cavity depth. Don't compress it. Confirm the continuous insulation thickness and continuity, and coordinate the WRB and air barrier penetrations and flashing. And the best practice in one equation. Cavity bat plus continuous exterior insulation equals better whole wall thermal performance. Slab edge or perimeter insulation. This is rigid board insulation, typically XPS or EPS, installed on the exterior face of the foundation at the slab perimeter to reduce edge heat loss. Why does the slab edge matter so much? Because the slab edge is a major heat loss path. The concrete is exposed to exterior temperatures, and concrete is a decent conductor. So the edge of your slab is basically a thermal bridge straight to the outside. In the detail, you can see the rigid board running down the foundation face, with the red arrows showing the heat loss at the slab edge that the insulation reduces. There's also an optional horizontal insulation extension out under the grade for added performance in colder zones. Most common in slab-on-grade construction and often required by energy code in colder climate zones. Installation note: protect the exposed insulation above grade with an approved finish or cover board, because rigid board above grade can be damaged and degraded by UV and impact. Your CM coordination checks. Verify the code-required R value and insulation depth. Coordinate termite inspection and protection requirements where applicable. That's a real conflict, because foam at the slab edge can hide termite pathways. Confirm durability and UV protection at exposed edges, and don't leave gaps at the slab-to-wall transition. The code note at the bottom is fair. Slab edge insulation is more commonly required in colder zones, but it still improves comfort and energy performance even here in a warm climate. Cathedral ceiling or insulated sloped roof. This is where there's no attic. The ceiling follows the roof slope, and it's one of the highest risk assemblies for moisture, so it requires careful design. There are 3 common approaches, shown across the slide. Option 1, the hot roof, continuous rigid board above the roof deck. The continuous insulation keeps the deck warm, which minimizes thermal bridging and reduces condensation risk. Option 2, an unvented assembly with closed-cell spray foam against the underside of the deck. Closed-cell SPF provides insulation, air barrier, and vapor control in one layer when the thickness is designed correctly for the climate. Option 3, a vented cathedral assembly. Bat insulation below a vent space, with rigid board above and a baffle maintaining a continuous ventilation channel from soffit intake to ridge exhaust, and you do not block that channel. The critical coordination box states the danger plainly. No vented airspace plus insufficient R value on the cold side equals condensation risk. Hybrid assemblies require careful dew point control, and you verify code-required R values and the vapor retarder strategy by climate zone. The CM and inspection notes. Do not compress bat insulation. Continuity of the air barrier is critical at the ridge, eaves, and penetrations, and mechanical, lighting, and vent penetrations must be sealed and coordinated. The note at the bottom is honest. These details are simplified. Follow manufacturer instructions, local code, and hydrothermal design best practices for your climate zone. Cathedral ceilings are where you bring in the engineer if there's any doubt. Below-grade foundation walls. 2 options, and the sequencing differs a lot between them. Option A, exterior insulation, rigid board on the exterior face, outside the waterproofing. Option B, interior insulation, rigid board or closed-cell SPF on the interior face. On the exterior side, reading from the soil in. Backfill, a protection board which is required before backfill, the rigid board insulation on the exterior face, the waterproofing or damp-proofing membrane against the concrete, a drainage board or drainage mat, and a perimeter drain, the weeping tile, at the footing. That's a lot of layers in a specific order, and the protection board exists specifically so the backfill doesn't tear up your insulation and waterproofing when it goes back in. On the interior side, you put rigid board or closed-cell SPF on the inside face of the foundation wall. Simpler, but watch the cautions. Interior foam may require a code-required thermal barrier or finish cover, typically half-inch gypsum board, because exposed foam is a fire issue. Exterior insulation must be protected during backfill. Coordinate the waterproofing, drainage, and insulation sequencing, and verify compatibility below grade plus termite and moisture considerations per project. The note at the bottom. Interior rigid board must be covered per fire code, and exterior installation typically requires that protection board before backfill to prevent damage. Last location, the crawl space, and this one has a clear right and wrong way to think about it. There are 2 strategies, and you pick one. You do not mix them casually. Strategy 1, vented crawl space. Insulate the floor above the crawl space and leave the crawl space vented to the exterior. Strategy 2, unvented or conditioned crawl space. Insulate the perimeter walls, not the floor above, and seal the vents to condition the space. In the vented version, bad insulation goes at the floor above. The crawl space stays vented with exterior vents, and you air seal the plumbing, wiring, and duct penetrations in the floor and protect pipes and ducts from cold air exposure. In the unvented and conditioned version, you insulate the perimeter walls, air seal the rim and band area, seal the vents and air leaks, extend and seal a ground vapor retarder up to the wall, and you bring the crawl space inside the conditioned envelope. The unvented approach is often better for moisture and duct performance. Best use. Vented is common in older construction. Unvented gives better moisture control if it's detailed correctly. Key risk. A vented crawl space can mean cold floors, frozen pipes, and duct losses. An unvented crawl space risks code compliance issues and incomplete air sealing. CM check. Verify the insulation location matches the design intent, confirm vapor retarder continuity, and coordinate local code requirements for the crawl space strategy. And the important line, which I want you to remember, do not mix strategies casually. A crawl space should be detailed as either vented with floor insulation or unvented and conditioned with perimeter insulation and sealed vents. Half and half is how you get moisture problems. Here's Participation Assignment 12, the Insulation Selection and Thermal Resistance Mini Case. 5 tasks, and they map directly to what we did today. Task 1. For 4 building conditions provided: cold climate, hot climate, marine humid, and mixed climate. Select the appropriate insulation type and justify your selection. Use the selection logic from the type slide: cavity condition, moisture, air sealing, R value needed. Task 2. Calculate the total assembly R value for the 2-layer wall shown, using the values provided for each component. Interior gypsum R 0.45, fiberglass bat R 13.00, OSB sheathing R 0.63, exterior air film R 0.17. Add them in series, just like we did with the R26 wall. Task 3. Identify the compression loss issue in the described installation scenario and state the corrected specification. In other words, spot the R19 in A2X4 mistake and fix it. Task 4. Explain in 2 sentences why continuous insulation provides better performance than cavity insulation alone. That's the thermal bridging answer. And Task 5. Match 3 R value callouts to their corresponding insulation type and approximate thickness. Everything you need to answer these is in today's recording: the type slide, the R value calculation, the compression slide, and the thermal bridging slide. Submit it on Canvas before today's deadline. If you get stuck, rewatch the R value section. That calculation is the heart of the assignment. Before we wrap, here's what's ahead. First, complete Participation Assignment 12, the Insulation Selection and R value exercise, due today. Second, Quiz 9, Insulation and Thermal Performance, opens today. It tests R value calculations, insulation type selection, compression loss, and thermal bridging, all for our fair game, so review them. Third, tomorrow is Class 13, Division 08 doors, frames, and hardware. Door handing, hollow metal frames, throat size, backset, lock sets, and panic hardware. It's a heavy vocabulary day, so come in ready to learn a lot of terms. And fourth, looking to Thursday, Class 15 is drywall, paint, stucco, and EFS, and weekly test 4 opens after that class. It covers insulation, doors, windows, and all the finish wall systems. Your Week 4 priorities: finish Assignment 12 early, review R value and thermal bridging, and start preparing for the doors and hardware vocabulary. That's Class 12. Even though I'm not in the room, the material is all here. Work through it carefully, get that assignment in, and I'll see you in the next recording for Division 08. Take care.